Right, so in the previous video, we introduced ourselves to logic circuits and specifically the branches, sequential and combinational. Now we shall look at sequential in more detail. The first kind of sequential logic circuit we will be looking at is the SR flip-flop, and specifically the so-called NAND gate implementation of the SR flip-flop. Let's dive in. SR stands for set reset, and flip-flop is a type of logic gate circuit that is sequential and is specifically used for storing data in the computer, a form of memory or register, right? And we'll see how it's actually able to store data by taking a look at this circuit diagram and the values that are passed into it. Another feature of this implementation of the SR flip-flop, which is the NAND gate implementation, is this thing called active low, which means that the gate activates when one of the inputs go from 1 to 0. That is, one of the inputs turns low, not high. We'll see how this works also in more detail soon. Now, to understand how the NAND gate system works, we need to first realize the NAND gate's truth table. A NAND gate is basically an AND gate, but the output is inverted. So what that means is 0 and 0 is 0, but its invert would be 1. 0 and 1 would be 0, its invert would be 1 again. 1 and 0 would be 1, which means that 1 and 0 passed through the AND gate and was inverted, which resulted in the 0 becoming a 1. Then finally you have 1 and 1, which is 1, but it's inverted, which means it's 0. So altogether, this is basically the truth table of the AND gate, but the final output is inverted with 3 1s and a 0 at the end. Now, to understand how this set reset latch works, we need to understand that this set reset latch has to be given a bunch of values at the beginning. What does that mean? We need to assume that S, R, Q and Q complement are already given values. Now, before we look at the values that are passed into the S, R, Q and Q complement, we'll understand what these inputs and outputs are. S stands for set, which is an input that is used to set the input or set the output of the latch or set the output of the flip-flop. We'll see what setting means, but it's to set the input, set the output of the latch to some value. Reset means to reset the output of the latch to some value. So if you repeat that, set means to set the output to some value. Reset means to reset the output to another value. Q is basically our output. Whatever set and reset results in is this Q. Q complement is whatever the opposite of Q is. And Q complement is not really that required for the most part, but we might just look into Q complement to realize what's going on in the logic circuit, whether everything is working fine. Now, just to dive deeper into setting and resetting, what actually it means to set this circuit is to turn the Q from a 0 to a 1. And as a result, since Q complement is the opposite of Q, it will go from a 1 to a 0. That's what set does. Set takes a 0 that is already in the Q and turns it into a 1. And it basically is now able to store a 1 in the Q. But the reset does is, it changes a 1 that is already there in the Q back to a 0. And a 0 that is already there in the Q complement to a 1. So setting means to set the gate or set the circuit to a 1. Resetting means to sort of get it back to a 0. That's actually what reset and set means. So hopefully that's clear to you. Let's now look at the whole concept of giving starting values to our logic gate. Now the idea is, guys, since this logic gate has this sort of cross-coupled connection, which means that the output of one gate influences the input of the other, there's no such straightforward way for us to understand what will happen at the beginning of the gate or beginning of the logic circuit. Because the problem is, let's look at this gate for example. It has two inputs, right? Let's consider that this input is A. The input A is not the only input that affects the output of this NAND gate. Q complement also affects the input and therefore the output of this NAND gate. But then how do you figure out Q complement? Q complement requires this other input that is coming in from this wire and also the value of Q, right? So then you're you're sort of reaching this stalemate where you can't figure out what to do next because we require outputs which are influenced by inputs. Therefore, what we need to do is we need to give this circuit a bunch of starting values. So what I'm doing is I'm giving the circuit a bunch of starting values which are S1, R1, Q0 and Q complement 1. I'm setting S to 1, R to 1, Q to 0 and Q complement 1. This is a set of starting values I'm assuming to have given to the circuit at the beginning. Let's write them down in this truth table. When S is 1 and R is 1, Q is assumed to be 0 and Q complement is assumed to be the opposite of that, which is 1. Now let's make one tiny change to our circuit. Let's make the set go from a 1 to a 0. 1 to a 0. The reset stays the same but the set goes to a 0. Let's see what happens. Set changes to a 0. Let's now look at very carefully what changes undergo inside this circuit and what outputs are a result of those changes. Now immediately this 0 goes through into the NAND gate, and the 1 from the Q complement passes into the NAND gate as well. And then we realize, okay, 0 NAND 1 based on this NAND gate truth table is 1. So then the Q value is no longer 0 but is 1. But then soon after, this 1 passes through as the input to the next NAND gate, which means you have a 1 NAND 1, which would result in 0. And the 0 passes through to the Q complement value, which in turn changes from 1 to a 0. And then this 0 goes back up, changes this 1 to a 0. 0 NAND 0 is 1, which means that this 1 stays as it is. And now you reach this sort of stable state where the values are where they are supposed to be. They don't change, right? They are all where they are supposed to be. And this is what we call the set operation, where the circuit goes through multiple stages of changes to actually realize Q equals 1 and Q complement equals 0. It's not just one change, it's sequences of changes that result in a final stable state. What does it mean to have a stable state? It means that the Q values don't change any further. It underwent a few changes and then now it's final. Q is 1 and Q complement is 0. So that's the next state. The next state is S became 1. Oh, actually S became 0, beg your pardon. S became 0 and R stayed as it is, and as a result Q became 1 and Q complement became 0. That's what we realized in the logic circuit above. Now let's do another change. Let's say that we set our 0 back to a 1. Let's go back to a 1. Let's make the set value back to 1. So we need to realize we can no longer have this starting assumption in our logic circuit anymore. We need to look at the next row based on the values that were produced from the previous row. So in the previous row the changes were S became 0, R became 1, Q is 1 and Q complement is 0. So let's write them down here. S is 0, R is 1, therefore Q became 1 and Q complement became 0. So this is our latest state. This state is what influences the next state. Okay, the next state is Q is 1, actually S is 1 and R is 1. Let's see what happens. S is 1. So we are going to set this back to 1. Let's see if there are any changes to the logic circuit as a result of this. There's a 1 passed in, it's no longer a 0. There's a 0 coming in from the Q complement. 1 NAND 0 is still 1, right? So the gate is still stable, but notice nothing changes. That's the beauty of this. As soon as you make both set and reset 1, the gate remembers whatever was previously put in it. Since the previous state was 1 and 0, it remembers 1 and 0 in Q and Q complement. So what happens now? It will basically stay 1 and 0. The next state I'm going to do is I'm going to make the reset back to a 0 and see what happens. If I make the reset back to a 0, guys, the one that is passed in here would become 1 and 0. 1 and 0 may change this Q complement to a 1. This 1 get passed through here. 1 NAND 1 would change this to a 0. 0 gets passed through here. 0 NAND 0 would still be 1. So you went through several stages and states, and finally you realize this stable state where the final states are set is 1, reset is 0, Q is 0 and Q complement is 1. Notice now the Q is back to 0. That's what it means to reset, right? Set means to set it to 1, reset means to set it to 0. So now the final statement of final result is Q is 0 and Q complement is 1. We are back at the beginning state. And here's an interesting thing. Let's imagine what happens if we set both S and R to 0. If you set S and R to 0, let's sort of clean this up a little bit. If you set S and R both to 0, what will happen? Again, before we look at S and R both setting to 0, we need to look at what the previous state's values were. S was 1, R was 0, Q was 0, and Q complement was 1. So, S1, R0, Q complement is 0, Q is 0, sorry, and Q complement is 1. That was the state, right? Okay. Let's make changes now. Let's make the set back to 0. What happens now? 0 and this 1, which is coming in from this input, or this output really, would result in 0 NAND 1, which would make this a 1. This 1 goes through here, 1 and 0 would make this a 1 as well. So now we are again in this stable state, and you might realize, okay, isn't that really not going to be a problem now? Isn't that okay? Haven't we reached a stable state? Yes, we have, but it's not theoretically correct. Q and Q complement are always supposed to be the opposites of each other, right? If Q is 1, Q complement cannot be 1. That's theoretically not possible. So therefore, this state is achievable, but it's not regarded as a valid state. So the final state when both S and R is 0 is that the circuit reaches this invalid state where both Q and Q complement is 0. Right? So there are several stages we realized in this logic, in this truth table. The first state is when both 1 and 1 are there for S and R. This is called the memory state, where it remembers the previous input. When S becomes 0 and R becomes 1, we reach the set state. When R becomes 1 and S becomes 1 again, we are again back at the memory state where it remembers whatever was previously put in it. If S is 1 and R is 0, it will reach the reset state. And when S is 0 and R is 0, it will reach the invalid state. Now going back to our beginning, remember how I told you that this logic gate implementation of the SR flip-flop, the NAND gate implementation, is active low. What does that mean? Notice that what results in Q changing is the input going from a 1 to a 0, right? See, when the set input went from 1 to 0, Q changed from 0 to 1. When the reset input changed from 1 to 0, the Q output changed from 1 to 0 as well. So what triggers changes in the circuit is when ones change to zeros. Ones change to zeros. Therefore, we call this active low, which means that the gate or circuit activates when the inputs are low, not when they are high. When they are high, which means they are both ones, it stores the data, it doesn't do any changes. But when one of the inputs turns 0, it makes changes. So if the set input changes to a 0, it sets the value. If the reset input changes to a 0, it resets the value. Right? And it's very important that you realize that you need to give the gate a starting configuration, which could be 1101 in this case, but it doesn't have to be 1101. It could also be 1110, which is also another perfectly valid memory state, right? It's another configuration that the SR flip-flop could be in if S is 1 and R is 1, right? So you can start off with any of these two configurations as long as you make respective changes afterwards. So if you start off with this other configuration, then the remaining rows of the table have to change. But if you start off with this configuration, the table is as similar as what you see on my screen right now. All right, very good. Right, so this circuit table can be simplified even further to what you see here, because in this table we have two memory states, right? We don't really have to show all those two memory states. We can represent them in a simplified form where when both are ones, it's storing data. When the set becomes a 0 and the reset becomes a 1, since this is an active low system, S is becomes 0, so therefore it will set a value from a 0 to a 1 in the Q output. Reset is basically when 0 becomes 1 for the set and 1 becomes 0 for the reset, which means basically the reset has become low now. Then the Q value goes to a 0, Q complement would follow. And the invalid state is when both items are 0, both inputs are 0, then the outputs are both 1s as well. Right, so this is the simplified version, basically gets rid of 2 memory states. Now the reason why this truth table was used to explain to you first is, notice how when you go from one state or one row of the truth table to the other, there is only 1 bit changes, right? 1 1, only this one changed to a 0, this one remained as it is. Here this one remained as it is, this 0 changed to a 1. Here this one changed to a 0, but this one remained as it is. Here this one changed to a 0, this 0 remained as it is. So we are making 1 bit changes, we are making 1 bit changes at a time, and that's really important because we can't make, or we don't recommend making changes to an SR latch such that we make 2 bits different at the same time, right? If you make 2 bits different at the same time, there might be this sort of race conditions which we'll look at, which is where both inputs are competing for the result, which is not a good behavior. So when we change our SR flip-flop, our inputs must be changed one by one. That's why this truth table that we used for debugging purposes was rather longer. But when you simplify this, at the exam you can write this truth table here, which is showcasing all possible of the 4 states of the SR flip-flop: memory, set, reset, and invalid. Alright, so that's about the SR flip-flop implemented using the NAND gate, which is an active low implementation. After that, we will look at the NOR gate implementation of the same SR flip-flop.